Okay. So, now what we have done? We have designed that analog filter Hs using transfer function of Hs, using Butterworth or Chebyshev, whatever you want. So, you design that filter transfer function H of S. Then what is required? I have to convert H of S to H of Z. So, how do I do that? Two methods, either bilinear transformation or impulse inverse methods. So, now let us discuss about the by impulse inversion. What is impulse inverse methods? So, what is objective? Design an IR filter having an unit response. Let us say if the H of S is my Laplace transform, then if the H of t is my time domain transfer function of the filter. Now, if H of t is the time domain transfer function, if I want to convert the same digital filter, then my the impulse response is Hn. So, my objective is to design a IR filter having an impulse response Hn, that is the sampled version of the impulse response of the analog filter. Is it clear? So, I am designing the analog filter. So, I know the analog filter equation HAT, and then what is Hn? Is nothing but a sample version, that is the impulse response of the digital filter. So, Hz is nothing but converting that analog domain to Z domain, which define my Hn. So, my objective is not only get Hz. So, Hz is not, there is a method, but my objective is that if I know Ht, I can get Hn by nothing but a sampling. If I have a signal St, then I get S of Nt is nothing but the digital signal is nothing but a sampling. So, time is sampled, discretized. So, I can say this is nothing but a discrete time response of the filter. Okay. So, let us say analog filter is HAS is equal to Ck by S minus Pk, where k varies from 1 to n. So, that means I am saying that I am to design a nth order analog filter which is HAS. Now, what is my objective? I have to find out what will be Hz. So, Ck is the coefficient. What is the Ck? So, I can find out the Ck value by a algebraic partial algebra, which is nothing but this one. Okay. So, now if this is my HAS, then what is the impulse response of the analog filter? So, HAT. So, HAT is nothing but a inverse Laplace transform of HAS. So, I can say HAT is nothing but a Laplace inverse transform of H of S. So, I take the inverse Laplace transform of H of S, which give me k equal to 1 to n Ck e to the power Pkt. Pk is the position of the pole. So, Pk is the pole position, S minus Pk. So, k equal to 0, S minus P0 into S minus P1 into S minus summation. So, k equal to 0. What is this? This is nothing but a C0 by S minus P0 into plus C1 by S minus P1 plus C2 by S minus P2, like that. So, that is my Hs. So, if the k is varies from 1 to n, then the order of the filter is n. Okay. So, now my responsibility to find out H of n. So, I know H of t is nothing but the inverse Laplace transform of H of s. So, H of s, I take the inverse Laplace transform, I get this one. Then what is H of n? H of n is nothing but a sampled version of H of t. So, H of n is equal to H of a sampled version, continuous time is sampled means n into t, t is called the 1 by sampling frequency or sample interval. Sample interval. So t, so continuous, there is a continuous time I sampled it at every t interval. So that's why t, this continuous time t is replaced by n into capital T. Okay. So which is equal to this one. Okay. Now what is Hz? So suppose h of n is my impulse response, then h of z is equal to z transform of h of n. What is z transform? Is nothing but a n equal to 0 to infinite h of n z to the power minus n. That is my z transform. Now I know h of n is this one, because this is the continuous impulse response, continuous time. I sampled the t into n into t. So this is my Hn. So I put this Hn value is in here. Okay. Once I put the Hn value, I get two summation. So if you see, Ck are related to the k. So I can say this k summation take out, and here all are related to the n. So I can say n equal to 0 to infinity e to the power pk nt into z to the power minus n, which is nothing but a pk t z to the power minus n whole to the power n. So summation sign n equal to 0 to infinite a to the power n, that is that can be written as 1 by 1 minus a. So it is Ck 1 by this one. Now this is my Hz. So Hz, if you see, I have a, this is my Hz, which is nothing but a summation of k equal to 1 to n Ck divided by 1 minus e to the power pkt into z to the power minus 1, which is nothing but a C1 by 1 minus e to the power p, let us say p1 t plus C2 divided by 1 minus e to the power p2 t, like that, dot 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 dot. Okay. So I can say z to the power minus 1. So I can say this e to the power pkt is nothing but a value of zk, because it is nothing but a z minus this one, z upper side z. So the pole position, the pole, digital filter pole is nothing but a e to the power pkt. What is pk? Pk you have given s minus pk, the pole position in s plane. So I know pk. If I know sampling frequency, zk is nothing but a e to the power pkt. So suppose I have an fs is equal to 8 kilohertz, then I know t is equal to 1 by fs. Then if I know pk value, I know the value of the zk. So this is my impulse invariance filter transfer function. So I know Hs. So if my Hs is equal to this one, Hs is equal to Ck by s minus Pk, then my Hz is equal to Ck divided by e to the power Pkt into z to the power minus 1. So I converted the s domain to z domain. Then what is the implication? What actually happened if I do that? Mathematically I can do that, very easy. But what is happen inside? So that means there is an aliasing effect. Why this aliasing effect come? Because I have a signal and I have sampled it. So if you see, any signal sampling is related to the aliasing. So I have to avoid aliasing, that is why I require an anti-aliasing filter. So this also I only have Ht and I have converted to Hn, But what is the anti-aliasing filter? What is that aliasing effect? Any analog to digital conversion required an aliasing effect. Why this aliasing effect is come? Now let's say I draw it, then it will be better than the show you the slide. Let's say I have a signal whose frequency response, I have a signal whose frequency response, I have a signal HAT whose frequency response H omega is look like this. Let's say this one. This is my frequency response. Now, when I make it sampled, if I sample this HAT by a sampling frequency Fs, then what is H omega? H omega is nothing but a Fourier transform of HAT. Now, HAT is periodic, Fourier transform is periodic. Now, in case of digital domain, the period is S defined by Fs, 2 pi. Sampling frequency is 2 pi, Fs is equal to 2 pi. So, if in mathematics when I say this one, then what will be happen? So, it is nothing but a HAN by Fs. So, Fourier transform of H of AT is nothing but a Fourier transform of H of A nt. If t is replaced by sampling, then f of t is equal to H of A. T means n by Fs. T is equal to 1 by Fs. So, I am doing the Fourier transform of n by Fs. So, this is nothing but a 1 by t. If this is the Fourier transform, which will come into j omega minus j k omega s, k equal to minus infinity to infinity. So, what is happening in physical? So, once I say that if how do I do sampling? Basically, I am passing this signal or multiplying this signal with an impulse whose frequency is Fs. Once I say I have sampled the signal, that means signal is periodic at after every Fs. So, highest frequency component is Fs. So, if this is 0 and if this is Fs, then there will be another repetition of the same signal. If it is this is minus Fs, there will be another repetition of the same signal. In communication, when you studied that let the omega m is my signal frequency. So, if I say cos omega m multiply by carrier frequency cos omega c, I get two components, omega c plus omega m, omega c minus omega m. So, when I say omega m has a two frequency component in plus omega m and minus omega m. So, in case of single frequency I said omega m. So, this will look like this. If the omega 0 to omega m is my the signal frequency. So, if this is my signal frequency response, then once I sample using sampling frequency Fs, I get this kind of series. So, there will be another again repeat at twice Fs, here also another repeat at minus twice Fs. So, this will be infinite in both sides because it is analog infinite filter. IIR response. Now, if you see, if this length 0 to Fs, this distance, and this is my omega m. So, if this omega m is twice omega Fs is less than twice omega m, what will happen? This kind of things will get. This is omega m, this is Fs, this is 0. So, there will be aliasing effect in both sides. Another again will be this side and again will be this side minus Fs. So, there will be aliasing effect. So, what is the requirement? When I design an omega p, let us say this is my omega p, if the omega p, and here also there will be omega p. So, omega p is my cutoff frequency. Let us say this is my passband edge frequency is omega s. So, suppose I want to, let us say take another slide, suppose I want to design this filter, let us say my filter frequency response is look like this. So, this is my omega s, let us say this is my omega p. Now, if this is so this side also same thing is there, negative side, this is minus omega, this side is minus omega, this side is plus omega. Now, once I multiply with Fs, once I sample it, then this omega is become sampling, small omega. So, in that case, at Fs also same thing will occur. So, there may be a aliasing. So, if the twice omega s is Fs is the Fs is so Fs is less than, if Fs is less than twice small cutoff passband or stop band edge frequency, then I can say both the filter stop band will be overlap in nature. So, there will be in overlapping. So, aliasing will be happen. So, I cannot design a filter where there will be aliasing is there. So, to avoid aliasing, my Fs should be such that so high that stop band attenuation is almost 0. So, I require a filter like this and my Fs is like this. So, I can guarantee the stop band attenuation is close to 0. So, there is no overlap. So, what is the limitation? The Fs should be very high. That means, T should be very low, 1 by Fs is equal to T. So, if I want to design a low pass filter, I have to think that what, suppose I want to say that, let us say I said Fs is equal to 8 kilohertz. Then maximum allowable stop band frequency is equal to 4 kilohertz. But the problem is stop band attenuation is 40 dB. So, if that attenuation is not 0, then also there will be a aliasing. So, let us say if I want to sufficiently allow it, so I can only design up to 2 kilohertz, let us say 2 to 3 kilohertz low pass filter, if the sampling frequency is 8 kilohertz. So, the impulse invariance methods, the main problem is designing a low pass filter that I have to choose sampling frequency well above, well high. That is the problem. Okay. So, that is explained in mathematics like this. So, aliasing occur, sampling frequency is less than the twice the highest frequency component of HAT. Is it clear? So, this will be look like this. This is the picture. So, this is my HF. So, this is repeated at Fs, again repeated at twice Fs. So, if you see, if this is my decaying like this and this is decaying like this, so this portion there is a aliasing. Aliasing portion is there. Understand? So, this what is the mathematical representation? This is F, Fs is equal to 0. One is it is plus Fs, that means F minus Fs, and it is this is minus Fs. So, it is F plus Fs, this side negative side and this side positive side. Okay. So, the impulse invariance methods, I can easily design the Z transform, but this T is determine the aliasing effect, because T is equal to 1 by Fs. So, if T is not sufficiently small, then aliasing can happen. To avoid aliasing, t should be sufficiently more small, that means sampling frequency should be sufficiently high. Okay? So, that is written in here, same thing. But see that in case of low pass filter, I have an aliasing effect, but in case of a high pass filter. So, what is the high pass filter response? High pass filter frequency response is this kind. This is your high pass filter. This is your high pass filter. So, high pass means all frequency after certain frequency. Now, if I multiply by Fs, what will happen? I will get same Fs at high pass. So, here also I get, here also I get, does not matter if there is a aliasing happen. So, I can easily design high pass filter using impulse invariance methods. Okay. Now, mapping of Z plane to S plane, whether this transform is stable or not. What is the mapping of Z plane to S plane? I am not going details on this side already I have explained. Okay. So, what is Z? Z is equal to e to the power st. If you see that Z is equal to e to the power pkt, position of the pole. So, S is the pole position. Okay. So, if my S is equal to, so this is my S plane, this is my S plane. So, this is A real axis and this is j omega axis, and this is my Z plane, Z plane. So, Z plane is defined by R. So, unit circle means R equal to 1. So, what is the stability criteria? My all pole must be inside the unit circle. Okay. So, the radius is R equal to 1. All pole must be inside the unit circle. How do I define a pole? Is nothing but a R e to the power j omega. That is discrete, normalized discrete frequency. And when I define a pole in here, so this is nothing but a, this is my pole. So, this is nothing but a plus j omega xy coordinate. So, S is equal to a plus j omega, Z is equal to R e to the power j omega. So, I can say since Z is equal to e to the power st, so R e to the power j omega is equal to e to the power at. So, S is nothing but a into j omega. So, e to the power at into e to the power j omega t. So, the real part, the magnitude part, R is related to e to the power at and j omega is related to e to the power j omega. That is why if you see, this omega is normalized discrete frequency, this omega is analog frequency. So, that is why the analog frequency, once I say that this is divided per sample Fs, T means 1 by Fs, then I can say it is not radian per second, radian per sample, which is nothing but a small omega. So, I know small omega is nothing but a omega t and R is equal to a to the R is equal to e to the power at. Now, why I said when I design the Laplace domain filter, the all pole must be in the left hand side. All pole must be in the left hand side. What is the meaning? Meaning is that the value of A is less than 0, because this is the 0 point. So, this is A is negative. So, if the value is less than 0, the value of A is less than 0, then I can say R can be within 1. So, R is less than 1. At A equal to 0, the R equal to 1. So, A equal to 0 means at origin that R equal to 1, S plane origin is nothing but a Z plane unit circle. So, if my all pole are in left hand side of the Laplace domain, I can easily say that that all poles are guaranteed within the unit circle. Now, if any pole in the right hand side of the Laplace domain is mapped to outside the unit circle, because if A is positive, A is greater than 0, then e to the power at is always, R is always greater than 1. Is it clear? So, that is the mapping of Z plane and S plane, that you have already studied in Z transform and S transform, Laplace transform. I just repeat that things. So, we see again, so Sz is mapping. So, that is the mapping which I explained is written in here. So, left hand side S plane poles are within the unit circle of the Z plane, and right hand side pole are outside the unit circle. That pole is okay. Now, how the mapping of j omega axis? How do I map the j omega axis? So, what is the meaning of this? That suppose this is my if my all are in j omega axis, let us say my all poles are in j omega axis. So, that means S is equal to j omega. Then how this will map to Z plane? So, let us real part is r equal to 1, then how it is mapped to the Z plane, or Z plane to S plane, how it is mapped? I know in discrete frequency, the frequency range is minus pi to pi. That is the normalized discrete frequency range. If the sampling so 2 pi is the maximum frequency, half 2 pi half is pi. So, maximum rate of oscillation is possible. So, the value of omega is minus pi to pi. Okay or not? Now, if you see, if it is pi by t, if the omega is equal to, what is omega? What is small omega? Is equal to capital omega into t. So, I can say that capital omega is equal to analog omega by t. So, if this omega is equal to minus pi by t, then I can say small omega is equal to minus pi. If it is equal to pi by t, then I can say small omega is equal to pi. So, this minus pi by 2 pi by t is all mapped with minus pi to pi. Now, let us say small omega is pi by t and also omega 3 pi by t. So, pi by t, 3 pi by t, which is more than pi, let us say. So, if it is 3 pi by t, then the omega, so what is the value of the small omega is equal to omega 3 pi, but 3 pi cannot be, because omega is varies from minus pi to pi only. So, this also mapped with these things. So, there is a many to one mapping. Is it clear? So, there is a many to one mapping. This is called aliasing, because all are compressed. So, they are overlapping in nature. Due to this aliasing is happening. Okay? So, in conclusion, we can say the mapping from analog frequency domain to digital frequency domain is many to one. It reflects simply the effect of aliasing, because analog frequency omega, capital omega, discrete frequency small omega. This mapping is many to one. It follows the frequency response of analog filter and the equivalent digital filter obtained by impulse and Fourier transform, that the analog filter must be band limited. So, that means HAT, when I say HAT I converted to HN, or HS I converted to HZ, that HAT must be a band limited to avoid aliasing, which is nothing but a minus pi by t to pi by t. That means Fs by 2. Highest frequency component, that is the property of analog to digital conversion. Highest frequency component must be Fs by 2. So, what is required? If you see in any ADC, the first step is anti-aliasing filter. So, if I use impulse invariance method, I have to guarantee that the design filter is band limited, means it is guaranteed that like an anti-aliasing filter. That means Fs is sufficiently high so that there is no aliasing is happened. Okay? Let us an example and then I stop, and then I can I can continue in the other methods also, then I will stop. Let us say I have a transfer function, this one. I want to use impulse invariance methods to convert Hz. So, what is the root? Root is nothing but a s plus 0.1 whole square plus 9 equal to 0. If I solve it, I get this is the root. Okay. So, this is the root. How many roots are there? Order of the filter n is equal to 2. Okay. So, I can say summation, this summation k equal to 1 to 2. So, I can say it is nothing but a C1, this will be C2, sorry. C1 by P1, let us say the P1 is equal to plus and P2 is equal to complex Z minus. So, C1 by this one plus C2 by this one. Now, how can I solve it? By algebraic expansion at Ck is equal to h of s into s minus Pk at s equal to Pk. I have already explained it, these methods. In earlier I have already explained it. Okay. So, from that I can find out the value of C1 and C2, 0.5, 0.5, and this is my Laplace transform. Then what is I known? I know Z equal to e to the power st, or I can say Hz is equal to k equal to 2 Ck divided by 1 plus e to the power Pkt Z to the power minus 1. So, I can say this equation, from this equation if you see that that Pk, value of Pk, P1 is equal to 0.1 plus 3j. So, I can say A is equal to 0.1 and omega is equal to 3, because S is equal to A plus j omega kind of things. So, I write down S equal to A plus j omega. Okay. So, I can say e to the power at into e to the power 3 jt. So, it is nothing but a e to the power at. Why it is minus? Because this is minus. So, this is minus 0.1, A is equal to minus 1, minus 0.1 into t and e to the power 3 jt into z to the power minus 1, and another pole is this one, only this one is minus, so this one is minus. Now, I get the Hz. Now, if you see the value of A is less than 0, because A is equal to 0 minus 0.1. So, that is why I can say R is less than 1. So, I can say Hz is within that unit circle. Okay. So, I have designed Hz. So, once I know Hs, I can get the Hz using impulse invariance methods. Okay. Now, if I say my cutoff frequency is this design, this cutoff frequency will be defined the position of the pole. So, if I say my cutoff, when I design this transfer function, I take the cutoff frequency omega p is equal to, let us say, 2 kilohertz and omega s is equal to 5 kilohertz. Then if I say to avoid aliasing, so around above 5 kilohertz, So I can say the T will be 1 by Fs, Fs should be more than 10 kilohertz. Okay, so that only the stop band are aliasing, but at least the transition bandwidth is not aliased. Okay. Now, bilinear method, mapping from the S plane to Z plane, I have already said that. Okay, so this is called, you can say this is called, I said, impulse invariance methods. Then there is another method which is called, you can say that is called, that method is called bilinear transform methods. Bilinear transform method. So what is the bilinear transform method? Bilinear transform is a mapping that j omega axis to the unit circle in the z plane only once. So what is the problem in impulse invariance methods? There is a many to one mapping of the j omega axis. In bilinear transform, this problem is solved, so the aliasing effect is not there. If I use conversion of Hs to Hz using bilinear transform. Okay. So how do we do that? We apply the trapezoidal formula for numerical integration of the differential equation. Let us see it and then you can understand. Let us say I have an Hs A B by S plus A. So I have to convert Hz using bilinear transform or trapezoidal formula. I will come to that. So if I say that H of As is equal to, so I can say H of As into S plus A is equal to B. So now if you see, if I have a system which has an Hs is my transfer function, if I apply x of S, I get y of S. So y of S divided by x of S is equal to H of S. So I can say y of S is equal to H of S into x of S. Okay. So if the y of S in time domain is yt, x of S in time domain is xt. Okay. So H of S is defined by B by SA. So I can easily write down this y of t into S plus A into yt is equal to B into xt, because this is nothing but I can say y of S, capital Y S is equal to B by S plus A into x of S. So this will be here B into x of S. So y of S give me the yt which is multiplying with S. What is the meaning of a S? S is called Laplace transform. S is nothing but a differentiator. So I can say this is nothing but a dyt by dt plus ayt is equal to B into xt. So I can say that the dyt by dt, take this one this side minus at into bxt. So I can say the differentiation of t is nothing but a minus at plus bxt. So what is the meaning? The instead of subtracting a finite difference of the derivative, suppose that we integrated the derivative and approximate the integral using trapezoidal format. So derivative is nothing but a, here you can see it is a differentiate. Instead of that, if I do the integrated, so I can say yt is equal to t0 to t y prime t plus dt. So this is okay. Think about trapezoidal, for the trapezoidal formula, that formula said that x1 to x2 fx dx is equivalent to half into x2 minus x1 f of x2 plus f of x1. That is called trapezoidal formula. Now, what I said, instead of differentiation of y by t is equal to minus a y t plus a t, a b into xt, I said I integrate this one to compute yt. Instead of take the difference, I take integrate differentiation of t to compute yt directly. So, what I do, yt is equal to compute is a t0 to t, first derivative into dt, d tau into y plus y0 t. So, this is the initial value, y0 is the initial, t0 is the initial value. Now, I said that t is nothing but a n of, so t is digitized. So, I can say y of nt is nothing but a t by 2 y prime nt, just put it this formula. So, instead of t I put n into t. So, it is t0 to t. So, I can say this the integration is nothing but a half of x2, x2 is nothing but a t, n of t, minus x1 is nothing but a t0. So, t0 is nothing but a n of t0, so that will be t0. So, it is t0 is nothing but a 0th instant, so let us say t0. So, this difference, so x2 minus x1 give me the half of t and is nothing but a y prime nt plus f of x2 and plus f of x1. So, f of x2 is y prime n2 nt. This is f of x dt plus this is x2. So, I can say y prime nt plus y prime nt minus t plus t0 is nothing but a nt minus t. T minus t, t0 is the initiation time. Okay. Is it clear? So, if it is that, so in case of in this case my x2 is equal to nt and my t0 is equal to nt minus t. Okay. So, x2 minus x1 will give me the t. So, that is why t by 2 into f of x2 plus f of x1 and this will be here. Now, if it is that, then instead of y prime nt, I can say that, so this is t0 is nt minus t. Okay. So, I can say the y prime t is equal to this I only know, this one, this already we know, this one already we derived. So, I can say that this I know. Okay. Then this I derived right now. Now, instead of this one I replace by this one. So, I can say y prime t, y prime nt is nothing but a minus a nt plus bx nt plus minus a y prime nt minus t plus bx nt minus t plus y nt minus t. Then I can say y of nt, just simplify this one, this will come, simplify, just simplify this one. Now, if I take the z transform both sides, so why I make simplify this one, I get this one. So, all the y in one side, all the x in one side. Now, I take the z transform. So, y n, so this is an a plus at divided by 2 into yz. Now, if you see one, this is okay, this is minus t. What is the minus t? Nt minus t. What is t? T is nothing but a 1 by fs, one sample duration. This is t, distance between the two sample. So what is the minus t means? It is delayed by one sample. So I can say it is delayed by one sample. So it is nothing but a z to the power minus 1 into yz. Yz is delayed by one sample. Similarly, here also this is minus 1 xz. Now I know hz is equal to yz divided by xz. Do that yz by xz. So it will be bt by 2 into 1 plus z to the power minus 1 divided by this one. So I get hz. Just simplification. Bt by 2 a 1 plus z inverse into at by 2. So all at will be z inverse will be there, and so all, if I make that simplify it, it will come in this form. B by a plus 2 into 1 minus z inverse divided by 1 plus z inverse. So what I have taken as an hs? So hs is equal to b by s plus a. hz is equal to b by this plus a. So I can say this is nothing but a s. If this is s, then I can, from this equation I can calculate what is z. Okay, and then mapping, then else is what? The mapping between s plane and z plane. So s equal to a plus j omega, z equal to r e to the power j omega. So s equal to this one I know. So I can say z equal to r e to the power j omega. So what is z? Z is nothing but a 2 by t plus s divided by 2 by t minus s. So r e to the power j omega, which is nothing but a t by 2 plus s, t by 2 minus s. So this I have known, this one is nothing but a how much? So 2 by t plus j omega divided by t by 2 minus j omega. So this is, let us say, a plus jb. This is a minus jb. So a plus jb divided by a minus jb. If I want to written in polar form, so this will be, amplitude is nothing but a square plus b square e to the power j tan inverse b by a. So this a plus jb, how can I write? A plus jb I can write in term of r into j theta. So here theta is equal to tan inverse b by a, and r is equal to magnitude root over of a square plus b square. So this is a, this is b. So this is the magnitude, and this is the tan inverse j, tan inverse omega t by 2, because b is omega. So b tan inverse b by a, b is omega and a is 2 by t. So omega t by 2. So j arctan means tan inverse omega t by 2. So arctan omega t by 2, and this is only the minus part is there. So only the theta will be negative, amplitude will be same. A plus jb and a minus jb both has the same amplitude, only the one is theta is positive, another one is theta is negative. So e to the power j theta divided by e to the power j minus j theta. So when I do it, e to the power 2j theta is nothing but a, so which is equal to, so r is equal to 1, because this one is cancelled. So I can say that r is equal to 1 and e to the power j omega is equal to e to the power j 2 tan, I can write tan inverse omega t by 2. Understand? So I can say omega is equal to is nothing but a 2 tan inverse, omega is equal to 2 tan inverse or arctan omega t by 2. Tan inverse 2 tan inverse omega t by 2. So what is, if I say this capital omega, so it is nothing but a omega by 2 tan is equal to omega by t, omega t by 2. So I can say omega is equal to 2 by t into tan omega by 2. Now if you see, omega is equal to 0, then z is equal to how much? 1. If omega is equal to infinity, z is equal to minus 1. So, z can varies to 1 to minus 1. So, whatever the value I can set, so z always z will be the within that unit circle. Infinite frequency can also map within that unit circle. So, the problem of impulse invariance methods is gone away. So, this is the conclusion. So, j omega exists within that unit circle. I have proved. So, entire range of omega are mapped into minus omega to plus omega. So, there is no error. So, there is no aliasing is there. Now, if A is less than 0, left half plane, then we can say mod of z is equal to less than 1 inside the unit circle. If A is greater than 0, then mod of j is equal to greater than 1. So, it is outside that unit circle. So, this will be not inside, this is outside. So, this is bilinear transformation. Now, take an example for your better understanding. Let us say Hs is equal to s plus 0.1, same example like that impulse invariance method, and here you take the same example. Only you have to put s equal to this one, what t is equal to 1 by fs. Now, let us say I say the sampling frequency fs is equal to 8 kilohertz, then you know the value of t. T is equal to 1 by 8 into 10 to the power 3. So, I get the value of the t. Then I know 2 by t value I know. So, that value is constant. Then 1 plus z inverse divided by, so I can say this is nothing but a, let us say 2 by t into 1 minus z inverse divided by 1 plus z inverse plus 0.1 divided by 2 by t 1 minus z inverse divided by 1 plus z inverse plus 0.1 whole square plus 9. Now, just simplify it, you will get this one. Simplify it, you will get this one. I think t equal to 8 kilohertz I have taken. You can simplify it. And if you see, then you can simplify that 0.00 z to the power minus 1. So, this is not a significant things. So, I can write 1 plus this one. So, that is the answer. So, that is called bilinear transformation. Simply S is equal to 2 by t 1 minus z inverse 1 plus z inverse. So, in summary what I can say, so when I design an IIR filter using analog filter approach, so what I will do first, my job is to, from the given specification of the filter, determine the Laplace transform of or Laplace transfer function of the filter. So, Hs I have to derive using Butterworth methods, Chebyshev methods or elliptical methods. Any one methods I can use, I can design that Hs. Once I get Hs, either I use impulse invariance methods or bilinear transformation methods to find out the Hz. Once you get the Hz, let us say you get the Hz is like this. This is another one example. Let us say Hz is equal to get s plus a divided by s minus b. Then how do I implement it? Very simple. Yz is equal to Hz into xz. So, let us say once this is Hs. Now, let us say after Hs I take the bilinear transformation, I can compute Hz. Hz is equal to, let us say 1 by, let us say 1 by z minus c. So, I know Yz equal to Hz into xz. So, Yz multiply by z minus c is equal to xz. So, Yz so this will be in the form of 1 minus z inverse, unless I have to took it like this way. Hz is equal to, take z common, so is equal to 1 by 1 minus c z inverse and z to the power minus 1. So, I multiply both sides by z to the power minus 1. So, it will be 1 minus c into z to the power minus 1 is equal to z to the power minus 1 into xz. So, I know that it is nothing but a y of n minus c into y of n minus 1 is equal to x of n minus 1. Implement in structure 1 or structure 2, this is x of n delayed by one sample added with this one. So, this is not xn is not there, only n minus 1, and then goes to this is y of n delayed by one sample multiply by c added with this one, structure 2 or structure 1, whatever you can do that. Here is an real life example. Design and single pole low pass digital filter with a 3 dB bandwidth equal to 0.2 pi using bilinear transformation applied to the analog filter Hs is equal to this one. So, what is omega c cutoff frequency? 0.2 pi. So, what is this one? H of s is equal to omega c. So, what is omega? Omega is nothing but a 2 by t tan omega by 2. So, I can say omega. So, this is cutoff frequency is normalized discrete frequency. So, this is small omega. So, I can capital omega is analog frequency is nothing but a 2 by t tan omega by 2. So, omega is nothing but a 0.2 pi. So, it is nothing but a 0.2 pi by 2. So, it is 0.1 pi. So, tan 0.1 pi 2 by t. So, 2 into tan 0.1 pi or 0.1 pi divided 0.1 pi divided by 0.1 pi divided by t. So, this value is 0.65 and t. Once I get this omega value, then what I can do? What I required? I said design a single pole low pass digital filter. I have to find out Hz. So, what is Hz? Hz is nothing but a omega c divided by t by 2 into 1 minus. So, s value of s you can put there and you can calculate that Hz. You do it in yourselves. Okay? So, I will stop here because the length of that video is increasing because of this is the concept which is there. You have to you just read it and go through this video, understand what is bilinear transformation, how do you convert it, and you do it. Okay? Thank you very much.